Preza from the University of Memphis, who is going to give a series of lectures, and the lectures will be on computational imaging. Today in the afternoon she will give two of those lectures, so let us welcome our speaker.
Thank you for inviting me to participate in this wonderful opportunity for everybody, and I hope that you're enjoying yourselves. And I know it's a bit cold in here, but you know, we just keep working our brains and keeping us warm, right? So I will attempt to give you an overview and a feel of this field of computational imaging from my perspective, okay? So I'm a professor, associate professor, aspire to become a full professor, I guess, one day, of electrical and computer engineering. So my background is both in electrical engineering and in computer science. And I also have a second appointment in biomedical engineering, so I collaborate with a lot of people on biomedical imaging applications. The research in my lab, which is a computational imaging research laboratory, focuses on computational optical imaging. We strive to optimize performance of computational imaging systems by deriving computations and integrating them with optical designs in order to develop systems, imaging systems with improved performance. And we have a number of collaborations in doing so with Professor Raphael Piestun as well. I will spend a lot of time discussing physical-based imaging. So we focus a lot about understanding the physics. So I'm delighted that many of you are physicists. I'm not, but this is something that we do, and we are into model-based imaging, and I'll talk a lot about that today. Particularly, we do statistical imaging, and I'll explain that in the slides to come. Or another way, these are all related concepts but slightly different, information theoretic image processing. One that we are interested in quantifying the amount of information that's being captured by the imaging system, and also the amount of information in appropriate units that is retained after the computations. We have focused a lot over the years on quantitative imaging for microscopy, so my second talk today, the second lecture, will be exclusively on computational imaging for microscopy. And we are interested in multi-dimensional light microscopy, so 3 dimensions, X, Y, and Z, over time, multispectral, different wavelengths. And I'll talk about fluorescence microscopy today, but we've also been doing a lot of work on phase imaging, from quantitative phase imaging using DIC microscopy, and I hope to talk about that in the upcoming lectures on a different day. We also have interest in hyperspectral imaging. We've done some work in the past, and on compressive sensing and imaging, but we don't have any funded projects right now in these areas. We are fortunate to have the opportunity to work with a number of collaborators, both in academia and in industry, and with students and postdocs. This list includes both past and current associations. And I just want to acknowledge all these individuals and their work, and also the mentoring that I have received through many of these collaborations. Okay, so I thought I'll start with a very broad definition of what is imaging science, right? So if you Google imaging science and go to Wikipedia, you'll find part of these words. it's a multidisciplinary field, and it's concerned with the generation, the acquisition of images, the manipulation of images, the analysis that you can do with producing images, and of course the visualization of images. Anything that you can imagine that you can do with images. And to carry out this type of research, as you might imagine, since this is multidisciplinary, we have people, researchers from physics, mathematics, computer science, electrical engineering, and also perceptual psychology, because humans visualize the images, right? So the beauty is in the eye of the beholder. So it's whatever you see in the image or whatever you understand. So that's also nowadays has become part of the imaging system, the human factor, right? So the applications that use images are plentiful, and I just thought I'll make it a little bit more interesting. Satellite imaging, of course, and I found some images of Montevideo from NASA. And also, I just want to show out the striking similarity between images with astronomy. So here's a cartoon galaxy, and from microscopy, like you see here, the mouse kidney image with fluorescence microscopy. So let's see. Now, I want to narrow this down a little bit. So I've talked broadly a little bit about imaging science, and my topic is computational imaging. So as you might be guessing, computational processing is a fundamental part of the imaging process, right? So you have a system that part of that system will be a computer that's doing some processing on the data, okay? And the kind of processing that we're talking about could be quite different, okay? So in some cases, our imaging system or our sensor might be generate, the measured data that we get might look like this image here, which doesn't show much at all, but it's supposed to be a sinogram from a CT scanner, so it just kind of looks kind of helical. And that's the measured data, but the desired image is the one that we get after the computations. And as you might know, with computed tomography, we have to get these images at different angles, and the processing is complex because you also reconstruct the object in the different directions to get the 2D image or the 3D image. The computations may be designed to improve unacquired images. So in some cases, we are able to measure data that resembles what we are interested to study, but may be blurred because of diffractions or defocus, as we had heard earlier today. And so our computations may be performing a deblurring operation and thereby improving resolution and contrast and brightness. And also, we, in this process, are able to extract quantitative information from the measurement. So if I'm able to correct all these aberrations and all these distortions, this measurement that relates to my underlying scene or object now becomes quantitatively meaningful. I can directly relate it to what I'm studying or looking at. And another area is the one that we create three-dimensional images using approaches or systems that are only able to produce two-dimensional images. So we have techniques or methodologies of acquire a sequence of two-dimensional images that we're then going to computationally process to develop a volume, a three-dimensional image. And I'm going to talk about in the next lecture on such a technique that allows us to create three-dimensional images using a non-confocal microscope that look like the images that we obtain from a confocal microscope. Okay, so yesterday we had heard about confocal microscopy and the improved resolution that you get with confocal microscopy in laterally and axially, and I'm going to talk to you today about a technique that uses a non-confocal instrument, but the computations perform the additional work that is needed to improve the resolution. Okay? And lastly, one could really summarize all of these efforts under a relatively newer field that goes by the name Computational Optical Sensing and Imaging, or COSI, that many of you are familiar from, especially if you're from the University of Colorado Boulder, right? Where in that effort, the development of imaging systems with improved performance is the goal, and to achieve that goal, we have to simultaneously design computations and novel optics that integrate from the beginning of the design to the end so that we can get improved performance. And the essence of this effort is really captured by the idea that we are deliberately producing imaging systems that deliver intermediate images that are encoded, if you will, in order to increase the information content in these images as defined by a certain application. And then the computations take into account this coding process or this deliberate artifact that we generate in order to produce the final desired image that has superior quality than if you had started out with a conventional system and then process that image. Okay, so it's a difference saying, okay, here's a black box, use it, figure out an algorithm or a computational method to improve the images. That's what we've been doing for a very long time, but now the idea is I don't have a black box anymore. I'm going to change it in a way that the output of this system is such that with my computations I can get better results. All right? So more flexibility there and more opportunity to create novel ideas that can give better results. All right, so for a very long time, I guess medical imaging and medical imaging applications have made a lot of progress, as well as fundamental research, of course. Before it goes into clinical trial, there's a lot of fundamental research to get us there. But traditionally, when people think of computational imaging, they might think of CT, which is computed tomography, or MRI, magnetic resonance imaging, optical imaging, ultrasound, nuclear imaging like positron emission tomography, right? And here's some representative images from these medical imaging applications. And these images come from this website, which is the Memphis Bioimaging Symposium website, one that I participate in its organization every year. And we have talks about all these medical imaging applications or methodologies. Now, as imaging, so in medical imaging, quantitative imaging has become very important. Okay, when we go to the doctor and there is concern about a tumor and how big is the tumor and is the tumor shrinking with how much chemotherapy or radio treatment does it take, quantitative measurement becomes extremely crucial, right? And so that's been well understood in the medical application, and it has evolved. In terms of the biomedical or biological study, we're not there yet. A lot of biologists are still using the microscopy in a very qualitative manner. You get an image, you look at it, you put it into Photoshop, maybe you're changing the colors or the contrast. Yeah, that looks like a structure I want to look at. But over the last 20 years or so, the dynamics are changing, and quantitative information in microscopy has become more important, and it's more urgent now to develop such techniques. And my work has focused on these three projects here: computational optical sectioning microscopy that I will speak about today, quantitative phase imaging from DIC microscopy, and structural illumination microscopy. These two I'll talk next on a different day. All right, so this slide you'll see a lot, okay, because I like it. Not quite, primarily because I'm going to use it as an outline for my talk, and it summarizes my methodology for computational imaging. This is specifically for microscopy here. And so what is this methodology, this fundamental idea? You see in the middle of this slide, there's this dashed line that I call the obstruction barrier, okay? What I mean is that on the left-hand side, I have these bubbles, right, that show what's going on in the physical world, okay? So the specimen on the slide here obeys some physical laws. There's some physics about the specimen. The propagation of the light through the specimen, through space, through the optics. There's some other physical properties here that can be considered or thought of. The light is focused by the optics of the microscope and by the camera, and then finally the computer where the data are stored and processed, right? And on the right-hand side, I show you my boxes that denote models that we develop. These are mathematical models, they're approximations that we develop from the best of our ability to understand the physics, and sometimes it doesn't represent our understanding, but we take some approximations so that we make these models tractable, so that we can actually program them on the computer and get some results, you know, in at least a few days, not years, right? So we have models that could describe these different components, and now these models become the abstraction, if you would, on which we base our algorithm development. And by algorithm, I mean computer algorithm, one that I can program. I can take this algorithm and program it and have a computational method, okay? So that's the idea. And then, of course, this algorithm or this computational method is used to process the data. So here I show you one image, the before processing, raw image, and after processing, and hopefully, you know, the difference that we see here between these two images is meaningful. And not only I can see the structures better, but they're, you know, I see structures that hopefully are real, right? And they're not artifacts generated by my program. So in order to answer those questions, there is another box here that's very critical, and that's the performance analysis. So I need to have a way to test the validity of these results. Okay, so I'm going to talk about this a lot more today. Okay, but I said that slide that I really like summarizes my methodology, but actually it's not unique to my thinking, but it actually summarizes the fundamental aspects of computational imaging as applied to the medical imaging fields and also to remote sensing, you know, other applications. So essentially, you can replace the word specimen with a scene, the word microscope with a sensor, right? And everything else stays the same. It's the same idea, right? So the fundamental aspects of computational imaging are the development of physics-based models, right? These models are based on the understanding of the physics. We try to capture what's going on in the real world. And then the development of model-based algorithms or methods that we can then design them in a way that's meaningful with our sensor. The hardware and the software need to integrate well in order to have a complete imaging system. Okay? So, and one thing that I should have mentioned here, so you see there are feedback arrows, which means that we take this, what we learned from the performance analysis, we go back and we modify our algorithm to improve it. And then we can also go back and improve our models, right? And maybe we can go back over here and improve the way that we measure our data, right? Or go back and change our sensor, our microscope, our optics, so that the data that I get are more meaningful for my computations. So it is a flexible kind of design, and one that we can improve. So you see here the same diagram, now different application, computed tomographic imaging. This is not my research, but one of my current collaborators, former co-worker or colleague at the Washington University in St. Louis, where I got my education, and one of my mentors, and he was very kind to share some of his slides with me that I'm going to be showing you today. So I will give you some examples. I'll use computer tomography as one of the examples. So just to recap then, in computational imaging, the goal is to use computational methods to undo degradations introduced by the imaging system, okay, or to decode the coding process that's been introduced by the system, okay. As I already mentioned, these computational methods require information about how the image is formed by the system, okay? And that's the information that we try to capture in our models and pass it to the algorithm or to the computational method. So the model-based imaging basically just implies that we are going to develop models that we're going to use to state our imaging problem that we are going to solve, right? Because these algorithms that we develop basically solve a problem. All models are approximations, right? And I have a few comments to make more about that. But we make assumptions, right, when we write down a mathematical model. And depending on how we choose these assumptions and how rich or complex the assumptions are, that's going to define the complexity of our model, how accurate our model is, and how complex it is to compute it. So there is clearly a trade-off between accuracy and complexity, okay? Now, I already mentioned that we're solving a problem, and there are actually two related imaging problems that are being solved in computational imaging, okay? So, on one hand, we have the physical world that I described, everything that takes place to produce the image. And over here, we have our observation space, where we have our measured data. That's where our measured data lives. And there is a forward model or forward problem that defines this mapping, right? How we go from the physical world to the measured data, the measured image. And what we're doing in computational imaging is developing solutions for the inverse problem. So given the data, we want to determine, right, or predict as accurately as possible what is going on in the physical world, right? So the forward problem describes computations or predictions of the output data from an imaging system, right? So if I have a CT scanner, my forward problem is one that I need to work on so that I have a mathematical equation that I can compute and get a result that will look similar or pretty much like the sinogram that I get from the CT scanner. Okay, that's what we mean here. Whereas the inverse problem defines the mathematical equations and the computations that are required so that I can predict or estimate the underlying object or scene, the thing that I'm interested in, from the measured data. And in both cases here, we're assuming that we have knowledge of the system's response. Okay? I mean, obviously there are methodologies, and we heard earlier today, that are called blind, you know, in blind approaches where you don't know the system's response, and you just need to work harder to do that. But here, let's just say we know what the system is doing. Okay? So, the forward operator, this forward model, takes us from a continuous infinite space, right, the physical world, or from our input, or you can call it object space, to the output or image space that clearly is a finite space, right, and often discretized. So the example of taking an image with a charge-coupled device or CCD camera, right, will give you a digital image that has a finite number of pixels, right? So that's what we mean by that. So clearly, this transition from the continuous infinite domain to a finite discretized domain implies a loss of information, right? It's obvious that we're going from a quantity with a certain amount of information to one that has smaller information content. And this information loss is what presents a difficulty in solving the inverse imaging problem. Okay? In many cases, that's a big challenge, and that's what makes it interesting in our field, in finding solutions to overcome this difficulty. Okay? So just to elaborate a little bit further about this non-uniqueness of the forward imaging model, you can think about two objects in the object space that can have exactly the same image. Okay, that can happen. All right. Why? Because of the properties of the system. If those objects have characteristics that cannot be imaged by your system, then because of loss of information, you're going to get an approximate result that could be identical. So it's given this image, then when you try to invert the problem, you have at least two solutions here, right? Or you could have a set of objects, let's say this is a set of objects, that have images that are not identical but similar, okay? So this is particularly so because there is noise in the measured image, okay? Because of the noise, we can have images that look similar but come from different objects. So this is a non-uniqueness in the problem. And because of this non-uniqueness, as you might have heard this word, the inverse imaging problem is ill-posed. Okay, what does that mean? Well, a problem is ill-posed if its solution is not unique. Okay, and I just argued that it's very plausible because of the loss of information that takes place with many imaging systems that I will not have uniqueness. So most of inverse imaging problems are ill-posed, or simply the solution does not exist, okay? Or it does not depend continuously with the data, which means that if my data changes a little bit, like there's some noise, and I try to find a solution, then the solution changes a lot, all right? You can get garbage out if you try to process noisy data. That can happen. So this definition of ill-posedness is the word, is one that characterizes many of the inverse imaging problems due to the loss of information that we described in the forward imaging process. and also because of the noise in the measurement, okay? And you might have heard the concept of amplification of noise. Anytime we try to do computations and in the presence of noise, that in trying to improve or recover information, we get this undesirable signal, the noise signal, that is not something that we are interested in, which increases or grows with our computations. Okay, so I'm just being somewhat vague at this point and not defining the mathematics behind it. Okay. So with this amplification of noise, the solution or the final image that we compute becomes totally unusable or unacceptable. Okay, so those are some of the problems. Okay, so are there any questions so far? All right. So although an accurate solution may not be possible in many cases, a good approximate solution may be possible or may be found. Okay, so the name of the game is that you have to settle for an approximate solution. Okay, which is a lot better than no solution at all, right? And this is possible by developing and using what is called regularization methods. Okay, and in an earlier talk today, there was talk of regularization approaches, and so really, if you just the non-mathematical and plain way to explain regularization approach or method is a method that inverts a problem, an imaging problem, or just, if you think about a matrix and you're going to invert the matrix, right, and it's an ill-conditioned matrix and you get garbage out. The idea is that you don't try to get the exact solution, but you try to get an approximate solution. One that avoids this inherent instability, if you will, of the ill-posed problem. So in most cases in imaging, what it means, approximating a solution, is that we give up some of the resolution. Okay, we have to settle for images that are somewhat a little more blurry. So that's the trade-off. You have to give a little to gain a lot, right? So a good approximate solution is one that can reproduce the data. All right, so you have the measured data, remember, and we're developing models for the forward process. So if I have a solution that I can pass through my model and it reproduces the data, right? That's what I want. I want to have a solution that has that property. And it also satisfies other constraints that are known about the physics of my imaging problem. Okay? So what are these constraints? For example, I may know that my object has a finite support. In other words, doesn't extend forever, right? I'm looking at a cell that's, it's about 10 micrometers wide and, 20 micrometers in thickness. Or my object is smooth, right? Its derivatives, if I take the derivatives of the pixel intensities or on the continuum, those derivatives are smaller than some quantity, okay? The values of my object, and what I mean by object, let's say if I'm talking about intensity here, the intensity values are not negative. That's a physical thing, right? I can't have negative intensity, right? As it was discussed earlier, what we measure is the modulus squared, right, of the complex amplitude of the field. So that's the intensity. It's always positive. So that's a constraint. And finally, my object might have some statistical properties. Okay, so it might have a mean or a variance of a certain probability distribution that I know. So all these kinds of information, prior information that I know about the object that I'm looking for are things that, that we refer to here as satisfying. We're trying to find a solution, an approximate solution that satisfies these constraints. And these constraints help us to do that, because it's not easy to just say, okay, the exact solution doesn't exist, let's find an approximate one, because there are many approximate solutions. So which one, right? So the way to find that approximate solution that makes sense is the one that's going to satisfy these physical constraints about the problem. Makes sense? Okay, so a little bit more about regularization methods. This idea of solving ill-posed problems can be handled or can be developed. You can take one or two approaches. One is called a deterministic approach or a deterministic framework, and in which case this leads to constrained optimization. So if you know something about optimization or minimizing some error between, like the squared error, usually between the data and the model, that becomes your cost function. Those are terminology in optimization. If that's what your model is, then you add to the cost function these constraints, and then you get a solution by having an iterative method. And I'll talk more about that. The other approach is to adopt a statistical framework, okay? In one that you consider variance and mean either of the object, and those are called Bayesian methods, or the statistical properties of the noise, okay? So in that case, when you're looking about how to fit your model to your data, okay, the way that is being done is by maximizing the likelihood of the data, okay? So you try to, in a statistical sense, find what is more probable, right, given this data and my model to be the underlying object. So it's in a statistical sense. And it depends. If I have Gaussian noise, if I'm assuming Gaussian noise being the dominant factor in my measurement, then this kind of approach again relates to a least squares methodology, minimizing a least squares error between the data and the model. If Poisson noise is the model that I'm using, then the maximum likelihood framework is one that provides a foundation, or is solved rather, with an algorithm that's called the expectation maximization algorithm, and also goes by the name Richardson-Lucy iterative method to people that contributed also in its development. So there are different groups that developed this algorithm, but essentially it's the same thing. And I'll talk more about the EM algorithm, but I'll try to keep it on the lighter side, okay? So let's see what comes next. This is, again, a summary of what I just said, the deterministic and the random model, put with the mathematical formulation here, that the difference being is that in the deterministic model, what you have as the measurement, you're considering it to be a function of your desired image. So we've heard earlier about convolution, right, of a Poincare function with the object, right? If my model is that, then that's a deterministic model. And even though I can assume that there's noise corrupting that convolution, it's still deterministic, and I can solve this problem by minimizing the mean squared error between the data and the model. But in the random case of the random model, we have to, we take into account more parameters, and we set it up as a likelihood function, and I'll talk more about that. And the constraints that I mentioned earlier are introduced in the likelihood setup in terms of penalties. So those are kind of the words or the terminology in the statistical imaging field. All right? So just to relate it back to physical phenomena again, if you think about photons propagating and interacting with the scene or the object, we have photon absorption, which is a random phenomenon, photon emission. In terms of fluorescence, perhaps, we have emitted light from the fluoroforms. We have photon collection by the optics, photon detection by the camera, right? And so all these processes are random, right? And so we can model all these random variations that take us all the way to the recorded data using some kind of a random model. And the Poisson point process model is one that has been accepted widely as suitable for photon emission and photon detection, and is particularly advantageous for low-light imaging. Okay, so I'll talk a little more about Poisson modeling. Okay, so here's the abstraction again, going from the object space to the image space. Remember, we had the forward model. And so in statistical framework for computational imaging, you still have the input and output space, but then this transition going between the two spaces is a density. It's a function that has a statistical meaning, right? It's more like a probability density. And the idea is that we are going to model with the probability distribution the number of photons and or particles that are being received at the detector at some given time, right? And there is this Poisson distribution that tells us what the probability of receiving n is, and it goes according to this equation, right? Where lambda is the expected value or the mean of the Poisson process or Poisson distribution. Okay? So this is a known model and one that can be used to determine the probability that a point in, or something in this space will arrive in the image space, or the counts that we have at the image space are determined rather by this distribution. And this kind of model is appropriate for fluorescence microscopy, for astronomy, for emission tomography, etc. So it's one that's being used in many of these applications, and a good reference is this book here on random point processes in time and space. Okay. And one that you might be interested or take a class with. Here's another. I forgot to mention now, I saw Pertero, but there's a book by Pertero and I forget the second author on inverse problems in imaging that I had on the previous slide, but this is a paper by that group. And in one that you can find a formulation, again, of this idea, where this is more accessible perhaps because they're using linear algebra to describe the imaging process. So Y is here, the data, right? And you can represent it in terms of a matrix vector form. So H is the matrix, is your imaging matrix that describes your imaging system. And X is the point, or the vector rather, that describes your object. And if this was deterministic, right, you would want to determine X given Y. And if you can invert H, you would do it, but usually you cannot, right? But in terms of statistical properties, then there's usually some background here added to this H times X. B, this is the background. And so every pixel in my image, we are assuming that it has a mean, that it's the value that my pixel value has, right? That the pixel value is the mean of the Poisson random variable. And so given age, I know what the system does. That's one of the assumptions that I mentioned earlier. And I make an assessment of that background value B. I want to determine X. And the basic, it's on the next slide, I guess. The basic maximum likelihood expectation maximization algorithm that computes estimates for X, right, is given by this equation, right? And what this equation does, it's better explained with this block diagram. So essentially, this is an iterative method, expectation maximization. So at every iteration K, I have some estimate for what X is, okay? So take the output here at iteration K, and that output, if I pass it through my forward model, right, it's going to give me a prediction of what the data should look like. So it's my operator operating on my estimate plus that background value. And then I use that to compare it to my actual measurement. And the comparison, you see, it's done by a ratio. I'm dividing my actual measured data by my predicted data. And that ratio now is a vector, right? And we call that it's back projected into the object space. So you see that I have this imaging operator H, but I have the transpose here, right? So I'm imaging it, but back into the object space. And that creates what is called an update. So this ratio that I get from here, I map it back into the object space, and I multiply it with my current estimate, and I get a new estimate. So now I have a new result, and it's I'm ready to iterate again. So K becomes K plus 1. And this goes on until we feel that we have the right solution. So here's that same block diagram here presented a little differently. So this is more like an implementation abstraction. How would you program something like this? So you start with some estimate. Usually we start with an image that just has ones in it. Everything, you know, in the image is one, a uniform image. For our initial guess, and then we create a model prediction of that. We compare it to the recorded image by creating this ratio. And if we don't have any recorded image to compare there, we just set it equal to 1, this ratio. So we have ways of, you know, if my measurement is really very restricted into a finite window, I can create solutions that extrapolate, right, outside that window. And then I project this ratio into the object space. I update my result. If there are constraints or penalties that I know about the size of the object or the value of the object, I apply them here, and then I iterate again, okay? So they're called penalties because we penalize unwanted behavior, right, in the solutions. All right, so how are we doing with time on this part?
Maybe 5 more minutes.
Okay, very well. So this is one of the papers on maximum likelihood estimation from incomplete data. Dempster, Laird, and Rubin was the other group that led the development of this algorithm, and Richardson and Lucy, they mentioned them earlier. So again, to recap, this is a numerical approach to determine the maximum likelihood estimate of some parameters given the data. So this part of the discussion here is a little bit, it's broad, you know, it applies to any kind of maximum likelihood problem, but I want to get to some examples from the medical imaging, and so maybe I'll just skip some of these, but because the EM algorithm has been very successful in these applications, CT and PET particularly, and in fluorescence microscopy that I'll talk in the next hour. So as I mentioned, it is an iterative method, and it performs 2 steps, an expectation and a maximization. And the key thing here, if you ever come across one of these algorithms, or you're in a position that you want to develop one of these algorithms, is that there is this notion of a complete data space. And again, what we measure in our observation or our data is most of the time incomplete, okay, for various reasons. But when we sit down to write a solution using this approach, we can come up with a hypothetical data space that is more complete, all right? So this is one of the advantages here. And it's a bit of an art, because you can create different expectation maximization algorithms for the same problem, depending how you choose this data space, okay? So that's kind of an interesting aspect to it. It's a design, right? And so as in all designs, there's more than one solution, right? In the sense of the approach. Okay, so again, the complete data space is one that captures the incomplete data space. So it's more, right? And there's a mapping in between those two, and that's then you know what that mapping is because you choose the space, and so you can get back, you can use your data to solve the problem in that sense. All right, so because I want to get to results, I'm just going to quickly set this up in the sense that this log likelihood that I mentioned, it's nothing but the natural log of a probability distribution. And this probability distribution is a conditional distribution of the incomplete data, the actual measurement, given the mean, lambda, of what you want to estimate. So you don't really have this, you want to estimate it, but remember at every iteration you have your best guess, okay? So at every iteration you have a chance to compute this log likelihood, and you do it in a sense that is maximized. And you can find a solution to this problem, it's a maximization problem, by finding the derivative and the derivative of the negative of this function, and setting it to 0. So you're minimizing its negative, which is equivalent to maximizing it. But it's very difficult to solve this problem analytically for images, because you have lots of parameters to calculate. Every pixel in your image, in your volume, it's a parameter, right? So you have thousands of parameters to estimate. So it's not a problem that you can solve analytically, and that's why we use the EM algorithm as a numerical approach via iterations to compute this maximization. And in the EM, as I said, there is an expectation, so it takes the expectation of this log likelihood and before it performs the maximization. So I'm fast forwarding this to show you some images before we stop. So it is an iterative method, okay, and in theory, as the number of iterations increases, the estimated parameters should improve, okay, and in fact, many of, the EM algorithm has been proven to reach convergence. In practice, though, when should the iterations be stopped? So you have this software, right, and you're cranking the iterations. And most of the times it says, okay, how many iterations do you want to run this? Or do you want to run this forever until the program stops by itself? And in practice, because of the noise present in the image, you cannot iterate or have the iterations go beyond a point. So you see here an example that comes from this paper, that it is based on simulated SPEC data, which is single photon emission computed tomography of a simulated thorax, and you start, the first iteration, you see what you have as a solution is really blurred, and as you increase the iterations 10, 15, things are starting to look really nice, or more resolved and clear, but then you see as the iterations of this algorithm progress, it gets noisy, or what they call salt and pepper appearance. So this is very characteristic of all EM algorithms, that your result will deteriorate. And so the approaches to deal with this, there are two. Either you stop the iterations early enough, you have to figure out in your application what makes sense, or use regularization, okay? And so you have to change then slightly the problem that you're solving, because remember with regularization, you're going to solve for a approximate solution. And this idea of incorporating this prior information on constraints is inherent it's easy in this framework, this maximum likelihood expectation maximization framework. First of all, the positivity constraint is inherent, because the comparison of the data in the model that I showed earlier is a division. We never subtract anything, right? So we never produce negative values as a solution. Other constraints are introduced as penalties. And other advantages of this framework that I want to also mention is that you can do joint estimation using multiple data sets from different imaging conditions. And some examples that I want to show you next and end with is from PET and from CT, okay? So PET, positron emission tomography, as you might know, has been around for a while, and is a methodology that has detectors around in a ring, and I don't have time or enough to discuss the physics of it, but basically there are different detectors here, and the measurement is obtained by having a source and a detector being across from each other, and the patient, or whatever you're imaging, has some type of a contrast agent, right, that is being imaged in this fashion, okay? So it's a nuclear imaging approach. The idea here that's being developed by my colleague and collaborator, but I'm not involved in this project, is that this is a new novel idea, and there is an insert ring, a smaller ring of detectors that is being inserted in the regular PET to concentrate on specific areas, perhaps the head or the neck or the abdomen of the patient. And so in this kind of setup here, so you see here we have an imaging system that has been used for a long time, and now there is a modification being made to the system in order to obtain better resolution, right, in these specific regions of interest that I mentioned. And by doing so, there are now 3 types of data sets that can be obtained, and it's called types of coincidence. There is the coincidence from the source to the detector that occur within the insert, this blue line. There is coincidences from between the insert and the outer ring or the scanner. And then there is the coincidences from the scanner to the scanner. So 3 data sets that can be pulled together jointly to yield a single restored image, okay? Now, the insert to scanner coincidences have a different geometry than the regular PET. In the regular PET, we have this parallel, let's say, from source to detector, and it's turning, whereas in the insert geometry, we have this fanning out, and there is attenuation and scattering that takes place, which results in a spatially variant system, okay, whereas if you don't have the insert here, you have a spatially invariant system. So the new computations now have been developed, set up the new joint log likelihood function to account for the 3 different coincidences or types of data sets that result, right? And then develop an iterative method. Remember, I showed you a basic form of an iterative EM method. This is a full-fledged method for this particular application that gives you an estimate for the underlying human anatomy, all right? And details, if you're interested in this, have been published in this paper, physical, medical, whatever, biology is called. So here's some images. This is from a small animal, prototype that has been built, and you can see reconstructions or EM results from using maximum likelihood EM from each data set separately, right? Scanner to scanner, insert to scanner, and insert to insert coincidences. And then insert to insert and insert to scanner, and then the result from jointly using all the 3D data sets. And you can see that the result here is somewhat better, particularly this one seems to have some artifacts more so than the others. And then this is a rendering of the 3D anatomy. Okay, so that was one application. And then here's another one just to illustrate. I mentioned about penalized approaches or regularized approaches. And here in this same insert pad device system, there is a penalty that's called the log Gauche penalty, and it's one that is represented, as you see here, by this mathematics. But basically what it boils down to is that you penalize the orthogonal neighbors, the green pixels, more than you penalize the neighbors that are the diagonals. And that's why these weights here are different, and these weights are entered here in this function. And again, you can go through that whole framework that we talked about briefly before and come up with an iterative algorithm that will result in images that you see here in the bottom row that are less noisy than the images that you see in the top row that are from the maximum likelihood expectation maximization algorithm that's not regularized. So here, as iterations progress, as I showed before, your result gets this noisy salt and pepper appearance, but if you use the penalty, you see that as iterations increase, you avoid this result, this appearance or this deterioration, and in fact, you are able to do better with smaller structures or structures that are sub-resolved. Okay, and details about these are in these papers. So I know this is more than 5 minutes, and I apologize, I'm coming to an end. But this is a CT application where there is dual energy data, and these sinograms don't show up, but basically this scanner is able to give two different results, and again, that vary because of the energy that is being used to obtain these, and these are jointly pulled together to produce the solution or the result. These are simulated results here. Okay, so lots of equations. So you see this, to do this kind of statistical restoration or reconstruction and get the algorithms, it takes a lot of mathematics and optimization, etc. I'm just showing you that to, not to go through it, but just, to appreciate rather that there is a lot that goes on there. Returning to this diagram, this approach works well, and the question is, what is the limit and when is there enough physics capture in this model-based approach? Okay, so as I mentioned before, we do the best to model as much of the physics, the biology, the chemistry, everything that we understand, and there are conflicting goals, the accuracy and the complexity. If we make our model too complex, then the algorithm that solves the inverse problem will also be too complex. So if you want to get a result today, you have to give up something. And then, of course, how do you need to quantify what this trade-off is. So I'm going to skip all of that because we don't have time, and I guess this will be archived and you can read them if you want to. But in conclusion, I went backwards, apologize. In conclusion, I hope that I gave you a flavor of computational imaging or model-based imaging in the sense that we have been using it and it relates to the medical imaging field. And the key thing here is that it requires modeling of the physics, and open questions always are, when is there enough physics? It is up to us to quantify the impact of the modeling errors and to quantify the trade-off between model and estimation error. Okay, so there is an error because of the approximations that we make in our model, but there's also an error in our inverse problem solution. So we have to figure out how to trade those off. And I spoke about the forward and the inverse imaging problems, and they're equally important, and all of these, the model-based idea drives the solutions for these problems, and the statistical imaging framework gives us the advantage and the possibility to develop algorithms that can produce better results than methodologies that are based on deterministic approaches and ad hoc kind of incorporation of smoothing solutions and results. And I gave you some examples real quickly just to give you a flavor. And I guess I'll stop here.
Questions?
And it's okay.
Well, if not, let's have some coffee and we will reconvene in 5 minutes
Yeah.
for the second part.
We're going to be caffeinated enough that